Question number 4 is where things get a little more interesting, because now you have exponential expressions on both sides, but they don't have a common base. Now when I say these are exponential expressions, I mean both of them have a base and they both have an exponent with an x in the exponent spot. But we know that this whole strategy we've been doing today is predicated on common bases. So it looks like we're going to need to rewrite the problem a little bit more carefully to ensure that we can do this common base thing. Now if I look at the numbers in the bases, I have a 4 and a 64. Generally speaking, you'll want to find a good base that you can write both of them with. In other words, a common base. It's not dissimilar to the idea of a common denominator, except the general rule of thumb is that you want to try to find the smallest common base that you can. Not necessarily because it's wrong if you find something that's not super small. It's just a good rule of thumb to follow. For example, 64 can have a base of 4. 64 is 4 cubed. So I can make a common base by simply calling 64 4 cubed. Now I could also make a common base by changing both of them. I could make 4 into 2 squared, and I can make 64 into 2 to the 6th, and I can do that as well. So you can basically find any common base that you want to. The general rule of thumb is go small, like I said. Or another kind of rule to follow, if you want to have some guidelines to follow, try to make one look like the other. And I'll write that out just so that way you have some sort of notes. The reason I'm sharing that wisdom is because sometimes you'll look at a problem and just not know and feel like, oh, do I have to? Like, do I have to look at every single part, every single possible base, and evaluate every possible number that goes into 4 and 64? So ask yourself first, if one of them's already pretty small, one of them's already a 4, can I make the other one into a 4? And it looks like in this problem, yes. Many of the problems that you'll do will have the same idea. So I'm going to keep 4 to the power of 2x plus 1 completely untouched. It already has a base of 4, and that looks good. But I'm going to need to change the 64. Now you'll notice I wrote parentheses, because part of this question is not going to change. And I want to make sure I emphasize here what's not changing. That power of x was always there. That power of x is not the issue. 64 is an issue because it doesn't match the 4. But the power can do whatever it wants to do. So I put parentheses there, and that's where I'm going to rewrite the 64 so it has the common base. 64 is 4 to the power of 3. So now the problem definitely looks more familiar. It looks more like the questions we were doing, with the exception of these new parentheses I just threw into the mix. So this is where a good rule of exponents can come in, because I don't think the parentheses are going to help much, but at the same time, we need to notice that we've just introduced a new exponent onto the right-hand side of the equation, and there was already an exponent there. And we have to remind ourselves that if we introduce a new power with an existing power, we need to think about how those exponents interact. And the rules of exponents dictate that if you have a 3 on the inside power, an x as the outside power, those two powers will multiply each other. So we'd have 4 to the power of 3x on the right-hand side. The left-hand side still hasn't changed at all, so 4 to the power of 2x plus 1 remains. But now that I'm looking at it, I have something that resembles the previous problems, the ones that seemed so easy. I have 2x plus 1 on the left that needs to match 3x on the right. This is where it gets a little bit trickier to solve with mental math, because now that you have 2 different x's, it might be a little bit more to juggle. So taking the algebraic approach might be a good one here. We could simply say 2x plus 1 equals 3x, and we can solve that like it's its own little equation. Of course, you can still solve in your head, that's totally fine. But if you want to simply subtract 2x, for instance, and have 1 equals 1x, so that means x is 1, that might be an easier way of doing it for those of us who don't like to juggle multiple variables in our head. In any case, it looks like we're getting x is 1. Now, as a good rule of thumb, you should either have the answer key available or be prepared to plug in your answer to the original equations and make sure it works. So 4 to the power of 2 times 1 plus 1 equals 64 to the power of 1. I'm just verifying to make sure this works. 2 times 1 is 2, plus 1 is 3, so I have 4 to the power of 3 equals 64 to the power of 1 is just 64, and we know that's true. 4 to the power of 3 is 64, so that checks out. Our equation looks good. Now make sure that that idea makes sense. Make sure that you're thinking about that idea. Because question number 5 wants you to adapt that strategy to a similar looking, though not identical, problem. Try it without watching the next video and see if you can do it. And if you can't, then watch the next video in this playlist and I'll walk you through it.